So the last video focused on how to use the separation of variables method to solve a first order first degree equation. In this video, we are going to use the separation of variables method to solve another kind of differential equations which are indeed reducible to this separation of variables method. So suppose we have a differential equation like this, where dy dx equals to some function of ax plus by plus c. This means that this function here is a composition of two functions. Among them, the one of the functions is linear, and that function, suppose we have a composition like this, f composition g. So f function can be anything, but this g function is the linear expression. Okay, so what we are going to do, we can substitute this ax plus by plus cz, not cz, only c as suppose z. Okay, so if we differentiate here, we will obtain a. We are differentiating this with respect to x. So here we will get a. After that, b into dy dx, c will become 0, and here we have dz dx. So from here, dy dx equals to dz dx minus a 1 by b. So this equation will become like this. If we substitute this term, this dy dx equals to term in the original equation, we will obtain 1 by b dz dx minus a equals to f of z. So the ultimate form will become like this: dz dx equals to bfz plus a. So now we can use the separation of variables method. We can take this term, this b plus b into fz plus a term below dz, and we can take this dx term to here. So after that, we can use the separation of variables method and integrate these terms. So now let us come to some examples. First, we have this equation here. So here we have again, so here one function is x plus y plus 1 and another function is the square function. So the composition of functions, f composition g, here the fx function is x square, and again the gx function is the linear function. So what we are going to do, we are going to substitute x plus y plus 1 as z. This will, after differentiating, this becomes this. Okay, so ultimately the dy dx equals to dz dx minus 1. So if we put this dz dx here and x plus y plus 1 as z here, we will obtain dz dx minus 1 equals to z square. So dz dx equals to 1 plus z square Now we can separate those variables z and x, and ultimately we will obtain dx equals to dz divided by 1 plus z square. So x equals to tan inverse z, and z will become, we have substituted z, so we need to again make it original. So tan inverse x plus y plus 1 plus c. Here should be a c also. So this term, this expression, so this is the solution of this differential equation, and this contains an arbitrary constant, as we have the first order differential equation. Now moving to the next problem. We have this one here. So again, there is sine of x plus y and cos of x plus y. So we are going to substitute the linear term. So here the linear function is x plus y. So we can substitute it as z. So after differentiating, it becomes dz dy dx equals to dz dx. So dy dx equals to dz dx minus 1. So if we put this dy dx in here, and again x plus y as z, x plus y as z, we will obtain this dz dx minus 1 equals to sine of z plus cos of z. So dz dx equals to 1 plus sine of z plus cos of z. So now we can separate these variables. So it will become dz divided by 1 plus sine z plus cos z equals to dx. Now we can integrate these things. So x equals to, now here is this form, this form. So if we have an integration of this form, what we are going to do, we can use the sum multiple angles formula for sin x cos x, and we after that we need to substitute tan, as the sum multiple formulas for sine and cos, there is a formula involving tan. So we will obtain a sec squared term, and we can substitute that tan in this formula. So we have dz divided by, wait, let me erase it, 1 plus sine z plus cos z. Okay. So x equals to integration dz divided by 1 plus. Now the submultiple formula for sine z has this form, 2 tan x by 2 divided by 1 plus tan square x by 2, and the cos z has this form, 2, no, not 2, there is 1 minus tan square x by 2 divided by 1 plus tan square x by 2 So it will become integration 1 plus tan square. We can take it in the numerator, tan square x by 2, not x. This should be z. Z, z, and here is also z. Dz divided by, so 1 plus tan square x by 2, 1 plus 1 minus tan square x by 2 plus 2 tan z by 2. So we have this 2 plus 2 tan z by 2. We are only simplifying this expression. So 1 plus tan square z by 2 will go up here, and if we add these terms, the the numerator of this term will become 1 plus tan square z by 2 plus 2 tan z by 2 plus 1 minus tan square z by 2. So 1 tan square z by 2 and minus tan square z by 2 will get cancelled out, and 1 plus 1 will become 2 plus 2 tan z by 2. So here integration 1 plus tan square z by 2 will become sec square z by 2, and below we have 1 plus 2 into 1 plus tan z by 2 into dz. So if we substitute this 1 plus tan z by 2 equals to, say, there is already a y, so differentiation half, as there is z by 2 here, will be a half sec square z by 2 dz equals to d. So there is already a sec square z by 2 divided by 2, so it will become du divided by 1 plus tan z by 2 will become u. So the integration is log mod u plus c. So u will become log mod 1 plus tan z by 2 plus c. So x becomes log mod 1 plus tan x plus y by 2 plus c. So this is the solution of this differential equation. Next we have this problem here. So let us now write it in this form. Dy dx equals to 1 by cos of x plus y. Again we can substitute x plus y into z. So we have 1 plus dy dx equals to dz dx. So dz dx minus 1 divided by 1 plus cos z. Okay. So dz dx equals to 1 plus 1 by cos z. So it will become 1 plus cos z divided by cos z. So now we can use again the separation of variables method, and we will obtain here cos z 1 plus cos z dz equals to dx. So we can use the integration here and we will obtain integration dx means x, and this side we can do some tricks. So we can multiply the numerator and the denominator by 1 minus cos z. It will give this. There is already 1 plus cos z term in the denominator, and if we multiply by 1 minus cos z, it will give 1 minus cos square z, and it will become this cos z minus cos square z, the numerator, and the denominator is sin square z, and there is dz. So let us now go to the next page. X equals to integration cos z minus cos square z divided by sin square z dz. So it will give cos z by sin square z. We can write it as cosec z cot z. Cos by sin will become cot, and 1 by sin will become cosec. And also cosec square by sin square will become cot square z dz. So we know the integration formula for cosec z cot z, but we do not know the integration formula for cot square z. So we can rewrite this cot square z as cosec square z minus 1. So cosec z cot z dz minus cosec square z minus 1 dz. So it will give cosec z cot z. It will become minus cosec z. There is a minus integration cosec square z. So cosec square z is minus cot z. So it will become plus cot z. And there is plus integration dz. It will become z. So this should be z. So minus cosec z x plus y, and there should be a c, plus cot z cot of x plus y plus x plus y plus c. So it should be here. So x and x will get cancelled out, and we have y plus c equals to cosec x plus y plus cot x plus y. Now moving to the last problem. Here this problem is not explicitly in the problem dy dx equals to that term f of ax plus by plus c, but we can reduce it to that form. Here x minus y minus 1 into dy, and here x minus y plus 1 minus dx. Wait, this should be plus minus dy, and here it should be, wait, let me erase it. So if we take dx common out, so there will be x minus y and there will be a minus 1 dx, and for dy we have minus 1, and if we take this x minus y term here, it will become this. So dy by dx becomes x minus y minus 1, x minus y plus 1. So again we are going to substitute this as z. It will become 1 minus dy dx equals to dz dx. So dy dx becomes 1 minus dz dx equals to minus z minus 1, z plus 1. So dz dx will become 1 plus z minus 1, z plus 1. So if we simplify this one here, it will become 2z, z plus 1. So if we separate these, we will have z plus 1 by z dz equals to 2 dx. Now we can integrate these. So first term is 1. So integration dz is z. The second term is 1 by z dz. So it will become log mod dz. So log mod dz. And the last term is 2x plus c. Okay, so we can use the condition this y minus 1 equals to 0 here, and we can obtain the value of c. So we are going to do that. So the equation is z plus log mod z equals to 2x plus c. So let me write it. Z plus log mod z equals to 2x plus c, and y of minus 1 equals to 0, and z equals to x minus y. So if we put, okay, so let me write it this form. Log mod x minus y equals to 2x plus c. So the value of x is minus 1, 0, 0, 1, minus 1 minus 0, log 1 is 0, 2 into minus 1 plus c. So c will be 1. So if we just simplify it, it will become x minus y plus log mod x minus y equals to 2x plus 1. So we can do this. X plus y plus 1 equals to log mod x minus 1. So this one here is the solution of the differential equation. Okay. So in the next video, I will discuss about the homogeneous differential equation and how to solve those homogeneous differential equation. Thank you for watching. Please like and comment to this video and subscribe to my YouTube channel.